just permanent magnets, and each one of those contacts is a magnet. And behind that, there's a sphere. So when you have two magnetic spheres that come together, anybody used to or remembers the old Mac laptop where it doesn't matter how you attach the power? Remember? It could be either way, right? So if two spheres are connected, so this is part of that. And this is called a Wow cube. And you're going to see in a minute, I'm going to pass it around why it is called the Wow cube. So I'm going to start it by pressing this button on the charging station. And then this thing boots. So each one of these modules has a motherboard, has memory, has a gyroscope, and believe it or not, it sells on Amazon. Not like I'm advertising or anything, but my friend invented this toy, and it connects to your cell phone with Bluetooth. And as I said, this thing has gyroscope, so I'm tilting it, and it knows what I'm doing. So to start, it's not a touch screen. So to start the game, you tap it like this. Okay. You familiar with the game 2048? No? Have you ever played 2048? Nobody ever played 20? How about Cut the Rope? See, to go back, see, this is a button. Now there you go. So it goes back to the main menu. I'm going to pass it around. So here's aquarium. So there are fishes in there, and you can create your own game for this, allegedly. So here you can see the top is the sea. So now this is the top, and you twist it like this. So each side has 3 COM ports, 3 serial ports. Okay. There's way too much money that was spent on this, on the development and production. But if you go on Amazon and you search WowCube, you're going to find it for a lot of money. See, this is. Hold on. There you go. Okay, so what do we have here? We have American presidents, we have Cut the Rope, there's Labyrinth, Make a Wish, and I'm going to pass it around so you can play with it. It's okay. 400, yeah. That's, how much do you think it costs to make?
300?
No. I'm not talking about investment, like physical, the number. So there are 4 processors. There are 24 LCD screens, even though they're 2 inches. You got in the diagnostic mode? Okay. You gotta twist it. Oh, there you go. See, maybe you're not supposed to go. Yeah. Well, try the lava lamp. Try that lava lamp. No, wait. It's not a touch screen. Okay. This has to be on top. So like this. See, it goes up. Here. You see? Hold it. Now tap it. Somewhere in the top. Okay, now you can twist it, and once you twist it, the pattern is going to change. But there are some logical games. There are Space Invaders. There's Cut the Rope. There's different kind of games. To go back, you would shake it. But not as violent as I did. See, that's all it takes. Try the present. Here, this is the puzzle. This one. You go up, so it goes up. See? You do it. You do my favorite. Yeah, there we go. There's an Apple phone that you connect to this thing through Bluetooth. They invested quite a bit of time and money into the charging station, which has LEDs. And now it's basically like Alexa. They're supposed to put AI in it. I don't know why. The previous versions had bugs with charging. This one doesn't. But that's how it charges. See this blade here? It goes through. And I helped. My friend invented this main thing, which was the magnetic contacts. So those spheres are rotating and they're making electrical contact, but they're actually magnetic. Any questions? They used to sell, like the top version used to sell for, I don't know, $6.99? Yeah, pass this around as well so that you know what's inside. Again, behind this thing, there's a sphere. And initially, I'm working on a paper that, let's see if I have it here. I don't have it on this memory stick, but anyway, what was I going to say? Please note that the last exam is going to be on the 23rd of April. That is going to be the last time we're going to meet in person. Not on the 30th, but on the 23rd. I made a mistake. So this is during the last lecture, and the exam is going to be on paper just like the one on Tuesday. And depending on what the average score is going to be on the second test, there may be or may not be a bonus problem, but probably yes. Well, it's whenever it's graded, then they're going to come up. Right? I guess sometime after or during spring break, maybe. This is the disadvantage of the paper test, is that it needs to be graded by a human. Are you going to get partial credit? Which is a great thing, right? And the last day to withdraw is on 28th, I think. But before you withdraw, please come and talk to me. And I don't want anybody to drop. I mean, things happen, but you already paid the money for this class. You might as well finish it. You know. There's a way to adjust the volume if you go to the settings, but don't do that. Don't worry about it. It's okay. We'll be distracted for the whole lecture with this wild group. If you don't mind. You want to see it, you want to hold it, you want to play with it. Okay, so today's topic is ceramics. And ceramics is 10 to 15 times stronger in compression than it is in tension. In fact, ceramics is not very good working and tension. We're going to talk about defects and impurities and look at the phase diagram for ceramics and also look at the mechanical properties and how they're different from metals. Bonding. What is the strongest type of bonding? Covalent. And pure covalent bonding only happens between what and what? The same atom. But if the atoms are dissimilar, then there's going to be a combination of ionic and covalent bonding, right? So we have stuff from the left side and from the right side, and depending on what the elements are, there will be a certain percentage of the ionic character of the bond as we calculated versus covalent. And the percentage of ionic character is increasing with the higher difference in the electronegativity of the atom. So this goes back to the basics. And this degree of ionic character could be either small or could be either large. So for calcium fluoride, it's large. For silicon carbide, it's small because they're over here, next to each other. Okay, most of the ceramics are oxides, and oxygen anions are larger than metal cations. Right? Also, oxygen packs in a closed pack structure like an FCC, and also cations would fit into the interstitial site among the oxygen ions. There's something to be said about the notation, which may or may not come up in the slides. But if you say aluminum, that's a metal. If you say alumina, that's an oxide of aluminum and it is ceramic. The same thing for chromium versus chromia. So the ending changes and it's a totally different class of materials. So let's take a look at this relative size. We want to form a stable structure. And when a positively charged ion in the middle is smaller, it's not a stable configuration. When it fits exactly into the spacing, then it is a stable configuration, or when it is larger, it is also a stable configuration. So we want to minimize the number of positively charged neighbors to accommodate for this. And the other thing that needs to be considered is that we need to maintain charge neutrality, meaning that the overall charge for the ceramic needs to be zero. It's not like it's a battery, so you can get excess electrons. As a result, the chemical formula as A sub m x sub p, this stoichiometry allows for the charge to be neutral. So M and P here would be corresponding like calcium fluoride. Calcium 2 plus cation is the charge is 2 and fluorine is F minus. So for each calcium there are 2 fluorine, like this. Does that make any sense? Okay. Also, even though we consider ionic bonding as primary, there is a process of transfer of electrons. Remember how I was brushing my hair with glasses and picking up a piece of paper? Yes. So there's transfer of charge, and then after that there is a ionic bonding, which happens through Coulomb interactions. Let's see if changing the battery would help. No, let's see if I put it in the chart. And let's see if that's going to work. Yeah, look at that.
All right, the coordination number.
I guess this works, but I don't know what. Anybody, what is a coordination number? Yes.
Is it the number of atoms in a unit cell?
Number of atoms where?
In the unit cell?
It's the number of nearest neighbors. So the coordination number is the number of nearest neighbors around. And what we're looking at here is the size, right? We started to look at the size here. And this is shown to you in a plane, right? You can see the unstable and the stable configuration. So the size of this ions is really what is going to control the properties of ceramics. And we're going to do a calculation of the density based on that. So coordination number is increasing with the ratio of the radius of the cation to the anion. Alright, so here's the ratio and the coordination number. And if the ratio is less than 0.15, or just 15%, then it's linear. In other words, you can put one small atom between the other two. If the ratio of the radii is between 0.15 and 0.225, then in the plane we can form a triangle. And then in between those triangles there's a spot where that other ion can go. And there's a triangular configuration. If the ratio is between 0.225 and 0.414, then it's a tetragonal. So if you take three fingers like this and you put another one over here, then the space in between would comprise a spot for a cation to be in. And an example is a zinc blende structure, which is shown over here. You see the three faces of the FCC structure right here. This, and this. And then the corner, and then there's a spot in between, and that's where the cation fits. If the ratio of the cation to anion is between 0.4 and 0.7, then the coordination number would be 6, and it can occupy what's called an octahedral site. There are 4 on the bottom, 1 on the top, and the other one on the other side. So 4 in the plane, 1 on the top, 1 on the bottom, like this. An example is table salt or rock salt, sodium chloride with a D. And the last one is when the ratio is between 70% and 100%, then it could be cubic, like cesium chloride. Now please pay attention to this, guys, because initially it looks like, what you got there? Okay. It looks like it's not body-centered cubic. Can somebody explain to me why this structure is not BCC? Why it's not body-centered cubic? Because at the first sight it looks like it. You have one atom right in the middle of the cube. Which one? Here? It's right here in the dead center, right here. This? Well, no, they just tried to like make this transparent, which didn't come out very good. This is what you're looking at here. This is cesium chloride. The atoms have to be unique. So the cesium chloride structure is actually a simple cubic structure with 2 atoms per lattice point. Was it shut down? Just twist it. Twist it. Nothing happens? Okay, hold on. See, a processor needs a button. To start a processor, there has to be a button. But on this device, there is no button. The button is here. So you're going to start it again. Somebody just shut it down, I guess. Just to play. Second question, how much would you pay for a kid? I tell you what's the biggest advantage. You try to, every one of you try to tilt it, twist it. There's a mind-body connection. So when you tilt it, maybe it has some special applications for people with disabilities, somebody who had a stroke and they have to use their left hand more than their right hand. There would be a game that would force them to use their left hand more than the right hand. Were you born with a smartphone in your hands? Can you imagine the new generation that is born with a smartphone with their hands? The border between the physical world and the virtual world in people's minds is just fading. So you can ride a simulator, and you can crash your car in a car simulator. But if it happens in reality, the consequences are going to be different, right? I guess that's the reality check. But anyway, let's go back to this. Let us calculate the minimum cation to anion ratio. For the octahedral site. So in the plane we have 4 atoms. We have 1 on the top and 1 on the bottom. And you see here, this is the radius of the atom. So we can write that 2 radii of the anion plus 2 radii of the cation is equal to the square root of 2a. Why? Because this is the diagonal of a cube of the side A. And A is equal to 2 times R anion. So we can write, and the coordination number, by the way, is 6. We can write that 2 radii of the anion plus 2 radii of the cation is equal to the 2 times the square root of 2R anion. And then we can express the radius of the cation in terms of the anion as square root of 2 minus 1 times the radius of the anion. And once we do the math, we get the 0.414. 0.414. And you can see here that that's exactly the threshold for the octahedral site. And our model of the hard spheres works. Okay, bond hybridization is when there's more than one, or there's significant covalent bonding. So for the hybrid electrons orbitals, for example, if we take like silicon carbide, the electronegativity for silicon is 1.8, for carbon it's 2.5. So you already seen this formula to calculate the percent of the ionic character is 100 times 1 minus e to the minus 0.25. Those electronegativities subtracted squared, and that gives us 11.5%, which means that 11.5% is ionic character, the rest is covalent, which gives you sp3 hybridization, and as a result, silicon can occupy tetrahedral sites in the silicon carbide structure. An example, predict the crystal structure of iron oxide. First, we'll look at the ionic radii. The iron 2 plus is 0.077. The oxygen is 0.14, so we take the ratio, and that gives us 55%. 55%, we go in here and see that we are in this region, so it's going to be an octahedral site, and the structure is going to be rock salt, or sodium chloride, table salt. So based on this simple calculation, you can make a prediction of what structure the ceramic materials are going to have. Let's take a look at the example of sodium with the radius of 0.1 nanometer and chlorine, which is 0.18 nanometers. The ratio is 0.56. And you can see that the sodium cations prefer the octahedral sites here. Other materials rather than salt also can form this kind of structure, and this is called rock salt structure. Another example of a salt is KBr, and KBr is the same structure as NaCl. And we tried to study the reconstruction of the surface. This is a movie I made from a surface reconstruction. This is 4 by 4 microns when you start to basically scratch the surface with the tip of an atomic force microscope. Magnesium oxide and iron oxide also have the sodium chloride structure. You can calculate the ratio of the radii, and so this is oxygen here, which is larger with magnesium. The last example was between 73% and 93% is the AX structure, where this is a cesium chloride, where we have cesium right here in the middle, and that happens when they are very close in size. So cesium here has 8 neighboring chlorines. Let's see the VMSC. Here you can select different surfaces. And again, if you ever need to make any kind of visualization, there's Material Studio software, which costs a lot of money. For something simple, this easy simulations would do. AX2, which is fluoride structure. Calcium fluoride is an example. You can see when there's a big difference in the size, like uranium oxide, thorium oxide, and then there's also another example which is called anti-fluoride structure, where the positions of the cations and anions are reversed. So you need to know the charge of these ions as they would form the structure. Another type is called perovskite. And perovskite structure is ABX3. Example is barium titanate oxide. So titanium is the smallest guy. It's right here in the middle. When we're going to be talking about piezoelectric properties, this is the material in your piezo lighter, or the igniter for the Weber grill, or one of those. But you can see these oxides can get relatively complex in terms of their structure. Based on this sizing, we can also do the calculations for the density. It's a similar formula that we used before, except that we have more than one compound. We have the number of units per unit cell and prime times the sum of the atomic weight of the cations in the formula unit plus the sum of the weights of the anions in the formula unit divided by the volume of the unit cell and divided by the Avogadro's number. Because this is the atomic weights, and it's per Avogadro's number, which is 6 point what? 10 to the 23 atoms per mole. So 1 mole of the material contains the Avogadro's number of atoms. Silicate ceramics is very common elements. Most common elements on the planet Earth are silicon and oxygen. And then that's how you get sand. You go on the beach, that's what's going to be underneath your feet. And silicon fits, this is called SiO2 tetrahedra. And the chemical formula is SiO2 silica, and it's polymorphic. Because it has different forms like cristobalite and tridymite. So this is an example of cristobalite. As a result, the melting temperature is very high, about 1700 degrees centigrade for this material. This is why it has a lot of technological applications for high temperature. This bonding of the SiO4 4- unit. This is the building block and the unit. And you can see that it is accomplished by sharing the common corners, edges, or the faces. And this is an example of magnesium salt. Magnesium 2SiO4. Or here's an example of silicon 2 oxygen 7 6- in case of calcium 2 magnesium silicon 2O7, and this is silicon 3O9 with the charge of 6-. There are also other types that can be added to maintain the charge neutrality, like calcium and aluminum, and then this whole tetrahedra SiO4 4- is bonded to one another because it has its own charge. This allows to do the stuff with glass, and And glass is amorphous, as you remember. It's transparent. Fused silica has no but sometimes we can add network modifiers such as sodium, calcium, aluminum, or boron. Quartz is a single crystal. So here's the structure of a single crystal. If we add, it's called soda glass, or if you get it at Walmart, I think the brand name is Pyrex. You can change many different parameters of this material by the network modification. There are also layered silicates such as mica and talc. If you ever see, people that lift weights, that white powder, that's what it is. Mica is a natural material that is transparent, yet it can withstand very high temperatures. My friend got a stove. It's 100 years old, and it was sold by Sears Roebuck. And the price of that stove 100 years ago was $100, which was a lot of money back in the day. But the front window has mica, and he had no idea what it was. He actually punched through it with a metal piece. I said, "Why are you ruining your piece? You just bought it." It's not a single piece of glass because the windows are very small. But mica, it's naturally occurring material. You would literally take that and take the layers of that. You can purchase it commercially. Another example is clay. Colonite clay, where it has the alternative layers with Al2OH42+, like this. And I think I've seen something on this order in VMSC here. But the idea is that, how many of you have ever been to a clay class? Have you ever made pottery? Green ceramics? Because of the water, you can easily form it into a shape, and then you fire it, and then it attains its shape. Okay, diamond. This is the structure of diamond. It is the hardest material known to humans. It has tetrahedral bonding of carbon. And if it's large, it's a large gemstone, so it's allegedly is worth a lot of money. But you can see every other tetrahedral site is occupied. So even in diamond, there's still space. It's used as a cutting material, as an abrasive. Also, it can be made in forms of a thin film, like on cutting tools and medical devices to make it biocompatible. Another form, so polymorphic. You remember this term, what polymorphic means? grains. What do you think the difference is between diamond and graphite in your pencil? The structure. So the grains, and if it's a single crystal diamond, that's a gem, right? So it's a single crystal. But it has to do with the forms and different orientation of the atoms. The reason you can write with your pencil is because there are carbon atoms in the plane like this, which is super hard. A single layer of that would be called graphene. And in between the layers, there's van der Waals secondary forces. So as a result, this material acts as a very good lubricant. And it's also the reason why you can write with a pencil. And also the reason why you can erase it with an eraser after that. But chemically, there is no difference between your pencil that has graphite and diamond. It also has graphite. That also has carbon. Okay, defects. Two types of defects, similar to metals. Vacancies and interstitials. Vacancies is when you have both cations and anions, because there could be one missing, either or. And interstitial can be for the cations, and they're not commonly observed for the anions because they're larger relative to the interstitial sites. So here's an example of a cation vacancy, and here's an example of an anion vacancy. And here's an example of cation interstitial. So to do a anion interstitial would be relatively hard to do because it's going to be large and it's not going to fit in here. So the lattice distortion is going to be pretty high as a result. Two types of defects because they have to go in pairs for charge neutrality. One is Frankel pair, which is a cation vacancy and cation interstitial pair. And another one is called Schottky defect, which is a paired set of cation and anion vacancies. We can also calculate the equilibrium concentration of defects using this famous equation of the exponent, minus Q sub D over KT. I had a project Soviet Union. They take atoms and they put them in the nuclear reactor. And the neutrons in the nuclear reactor physically displace the atoms in the diamond. And they form Frankel pairs. Frankel pairs are, if you look at the picture here, is a combination of a cation vacancy and cation interstitial. You see? So for this atom to go back and restore its shape, energetically is relatively high. But when you have the cascade event of irradiation with neutrons, then the average lattice parameter is increasing. And then they've done it for the silicon carbide. If you ever want to measure the temperature in a jet engine inside a turbine blade, it would be relatively hard to do that. So here's a temperature plug, which is a piece of steel that undergoes recrystallization as a function of temperature and as a function of time. You can see the size. It's substantial. Here's a penny. This is the sensor, which is 300 microns. So this powder of sensors, single crystal sensors, was placed in the nuclear reactor. It was subjected to radiation for 1 month. And after that, it was taken out and calibrated using X-ray diffraction. So if you look at the lattice volume expansion versus the neutron flux, around 3 to 4% is the sweet spot. Silicon carbide is yellow. As a result of this irradiation process, it becomes black. And the reason is because the lattice parameter is changing. You can actually make it completely amorphous if you increase the volume to 8%. So, you would grow the crystal. You crush it into smaller pieces, sieve it, put it through irradiation calibration, install it on an engine, run an engine, and take those sensors out and figure out what the temperature was. Here's an example of a calibration curve that shows you the lattice expansion versus time of exposure for 600 C, 700, 800 degrees C. And the accuracy was pretty good. If we get the time to talk about thermal properties, have you ever seen a shuttle, the space shuttle? The thermal protection system is made from that. So these sensors were used for the Soviet analog of the Russian shuttle that was called Buran. It was back in the day of the Cold War and the space race. Anyway, here's an example of how cation, calcium interstitial can be accommodated for because of its charge in sodium chloride and there's regular salt, or it could be a substitutional anion impurity here, oxygen. Some of the applications of this can be in gas sensor. Because potentially you can make a device, electronic device using this. Ceramic phase diagrams are similar to the metal phase diagrams, except that you are dealing with oxides. So here's magnesium oxide and aluminum. And this is the percentage. So you can see that there's one eutectic here, another one over here. And this is for the high temperature applications, like if you want to make a furnace, for example, or something that can withstand 2800 degrees C. There aren't so many materials on this planet that can withstand very high temperatures. And ceramics are part of that. Okay, so why are ceramic materials brittle? Because of the bonding, and because of the structure, and because it's very hard to have dislocations in ceramic materials, and primary reason is it's hard to have dislocations in anionic solids because you have to maintain the charge, right? In polycrystalline materials, we have dislocations. In ionic solids, we don't have the dislocations. Fewer slip systems, and there's very large resistance to motion of half those planes of atoms per one another. How are the properties tested? Because the materials are brittle, it's practically impossible to do a tensile test, because once you start to grip, you cannot grip ceramics. Try grabbing onto glass, it'll be very hard. So it's done in flexural tests. Here's an example of 3-point bending, and the cross section can be either, it could be a cylinder, it could be a rectangular cross section, but you would get the force versus displacement, and the slope would be F over delta. And then for the rectangular cross section, the elastic modulus is going to be this ratio, the slope, times L cubed over 4BD cubed. D is the diameter, or F over delta L cubed over 12 pi R to the fourth for the circular cross section. I'm sorry, R here is for the circular section. R is the radius. This is for rectangular cross section. For that, you would need to basically have some sort of a micrometer, and I've built one for polymer testing. Which would also fit for this, although we haven't used it for ceramics yet. You take a regular micrometer, which has a resolution of 1 micron, and you can put your sample down here, and then on top you just put the weights. Very inexpensive way to test the mechanical properties by using the deflection test. Here's some examples. This is modulus, 300 GPa, 400 GPa. Glass is the same as aluminum of 69 or 70 GPa. And this is the fracture strength. Okay, the bonding in ceramic materials is primarily ionic and covalent, and you can calculate the percentages. The crystal structures are based on maintaining charge neutrality and cation to anion ratios. There are imperfections in terms of vacancies, interstitials, Frankel-Schottky defects, substitutional interstitial impurities that need to be maintaining their charge neutrality. And at room temperature behavior, we can use flexural tests for measuring the elastic modulus, or looking at fracture using the 3-point bend test. Any questions? Are you guys ready for spring break? What are you going to do? How are you going to relax? Sleep in? Approach of the material science in this class to control the process, to control the structure, to control the properties. So the same thing applies to ceramics, right? But first we need to classify it. This is the classification chart. Glasses, clays, refractories, abrasives, cements, biomaterials, carbon, and advanced ceramic. Engine, rotors, valves, and bearings, and I'm waiting to see when I will drive a car with a ceramic engine block. I'm waiting for many years, and it's still not here. Because that would essentially eliminate the need for lubrication if we can get an engine block made out of ceramics. The glasses. Glasses are everywhere, primarily because glasses are transparent. Clay, pottery and stuff, refractories, bricks and furnaces, abrasives, sandpapers, cutting, polishing, cements. Look around. Concrete is the main ingredient, is cement. Biomaterials, implants, you don't want to put anything into your body that's foreign. What happens if you put something into your body that's foreign? The body starts to reject it. You take medications to suppress inflammation, but inflammation is normal. What if you get, regular disease or virus or whatever, or infection? You need that. But because of the neutrality of ceramics, even in dentistry, zirconia or zirconium oxide dentures is so far the state of the art for different kinds of prosthesis. Because metal, if you put more than one, or even if you put one, which is an alloy, you automatically have a battery there because you have a salt solution and you get, we're going to talk about corrosion, but die blanks, you can do that if the material would be able to support this tensile force. Here are some examples of the dies. And the idea is to have this to reduce wear and have properties. What do you think of that? You think? How much are you going to buy it for so that you're going to be happy? They sell it for $3.99 on Amazon. How much is the price of a cell phone these days, like the cheapest? $700. What are you talking about? I'm talking about the cheap one. The one with the screen and the Android phone. $50. You can buy a cell phone for $50. It's going to have 500 megabytes of storage, but it's going to have an LCD display. So, how much do you think this module is? One of this module. There's a battery, there's a speaker, motherboard, memory, gyroscope, accelerometer. So $50 for this is reasonable to me. Times 8, that's how you come up with, what did I say, $3.99, $400? But the cost right now to make it is $300. This whole device. That's the cost. And I think it's all about how much it costs. It's not about whether you need it or not. If it's $99 at Walmart or $199, you know how the company would make money? Through the App Store. So they can even, just like Kindle, at some point they were giving out the devices for free, right? How do you create a business need when there's none? At the same time, gaming business is $1 billion business. How many of you have a gaming platform? Sony PlayStation? Nintendo? Okay. How often do you play? You don't have the time, you're students. But your brothers and sisters do. They find the time. Well, I can tell you that if when you're driving a car and you have a kid in the back of the car, this is the best way to keep them busy. So that you can drive from one stop to the other. DVD players. Yeah. You could do that. Anyway, my favorite game is 2048. And the problem is that this is not the latest version. I got one of the prototypes, so it's bugged. All right, guys, have a good spring break. Get enough rest, enough sleep.